Thank you. Okay, so I actually thank the organizers for the invitation and for having me here. It's really great to be in this conference. What I'm going to talk about today is probably a bit far from the theme of the conference, but yeah, in any case, this is something I would like to share with you. So this is a joint. So this is a joint work with my colleague at Tsinghua, Xie and Yan. So they're both working in mathematical physics. And so here comes some physicist background of this talk, which I learned from them. And you shouldn't expect more lots of detail from me on this. But so for them, if you consider 4D into superconformal field theory, whatever that means. So this physicist being the Viento, Piller, Rastelli, Van Reis, they associate vertex algebra. Okay, whenever you have a theory, you get a vertex algebra, and inside here you have a special class of theory which is called class S, and those are the theories which you deduce from a 60 to 0 superconformal field theory by put it on the like this already, like R3 cross S1 cross the Riemann surface C. Okay, and then to this theory, you have two branches. Like one is Coulomb branch and the other is Higgs branch, and you actually have some understanding of them for this particular class field theory. And for the Coulomb branch, it's described by Gaiotto, Moore, and Netz. It is given by the Hitchin system on your Riemann surface C. Okay. And then the Higgs branch, it's supposed to be given by the associated variety of your vertex algebra here. So this was proved by Arakawa. So this is like a mathematical theorem. And then for the purpose of this talk, we're going to be interested in yet a still more particular kind of theory, which is called generalized Argyros-Douglas theory. And in this case, the Riemann surface which came up is just P1 with two punctures. And on this side, we'll be looking at the vertex algebra, which are like W-algebras. Okay. So this is the setting we'll be interested in. And now, so our interest is like there is this physical expectation where, well, you have two branches of the same theory, and you somehow want to understand how the data corresponds well to each other. And one of such an instance is that they expect that the C star fixed point in some Hitchin fiber should match up with irreducible representations of W-algebras. Okay, and for example, there's like Fredrickson next established for so-called W and M minimal models, basically kind of W algebra in type A and in principle nilpotent case. And then Fredrickson, K, and Ye, they studied the case of affine SL2 and its reduction to Virasoro minimal model in some other cases. Okay. And then I talked to these two colleagues, and then at some point we just realized that the Hitchin fiber which comes into play in this story is some elliptic affine Springer fiber, which like kind of I've been playing with them for some time and then know them pretty well. And so then so therefore so we're able to establish some this desired bijection between the fixed points and irreducible representations for the affine Kac-Moody algebra at so-called boundary admissible level. I will tell you what they are. And then, so I will explain later that this admissible representations comes in study of Kac and Wakimoto. And the initial motivation for them was to generalize this modular properties for integrable representations of affine algebras. So this is a class of larger representations whose characters still have modularity. And then we give an interpretation of that modularity in terms of double affine Hecke algebras. And then at the end, I'll try to explain how to relate sort of reduction on fixed points via Stringfeld-Sokolov reduction to representations of W-algebras. Okay, so this is the plan of my talk. Any questions? Okay. If not, I will go on with lots of notations. So bear with me, but these are classical notations. So let G be a complex semi-simple Lie algebra, be a Borel subalgebra, and H Cartan. And then you take those on the Longland's dual side by putting a check on them. And then we know that you have a natural identification of the Cartan for the Longland's dual and the dual of the Cartan subalgebra. And what I'm going to use is that I will always be considering roots for G, and I view them as co-roots for G check. So this set will be denoted phi, and inside I have the set of simple roots, alpha 1 to alpha L, and they will correspond to simple co-roots for the G check side. And then W will be the wild group, Q will be the root lattice, and P will be the weight lattice. So like these are all on the side of G, and there will be co-root lattice and co-weight lattice to the side. Okay, and the setting we're going to be working with, so I told you I want to match some representations with fixed points in Fine-Springer fibers. So on the representation side, I will be working with affine Lie algebras associated to the Longland's dual of G. Okay, and then on the fiber side, I will take the Longland's dual of this affine Lie algebra. Okay, so in type ADE, you don't have any confusion. So G is isomorphic to G check, and then their affine Lie algebras are also isomorphic. But in non-simply laced type, you need to be careful. So if you take the Longland's dual of a affine Lie algebra, which is say of type BCFG, you will get a twisted affine Lie algebra, but whose underlying root finite root system is it's the root system for G. Okay. Okay. So then I got a bunch of notations for the affine Lie algebras. So I have as before had identifications between the affine Cartan of this Longland's dual side with the dual of the Cartan here, and then so this is H dual plus C delta plus C lambda 0, and then I had identification between H dual and H check as before, and K corresponds to delta and D corresponds to lambda 0. Okay, under this identification. And then I will only care about the real roots. So I'll consider so phi hat real is real roots for this Longland's dual of the affine Lie algebra. And then it identifies with real co-roots for the affine Lie algebra of G check. And then I have affine simple roots. And here, so simple roots, you add an alpha 0, and alpha 0 is delta minus the highest short root, which is denoted by theta s. Okay. And okay, and now if you write theta s as sum of the sum of simple roots, then your Coxeter number for this this dual affine Lie algebra is 1 plus the sum of AI, and here should be an L. Looks like an E. And this identified with the dual Coxeter number for the affine Lie algebra. And then I'll need a affine wild group, which is W's semi-direct product with the root lattice, and the extended affine wild group is W semi-direct product with the weight lattice, and they both act on these affine Cartans, and it's dual in some standard way, which I don't tell you the formula, but it's quite standard. So the Q was that is for the original G? The Q is, if you want, the Q is the root lattice for the original G. If you want to look at this side, it will be the co-root lattice. So, right. And finally, so I will care about representation for this G tag hat. So I'll be considering weight for them. And so on space of weights, you have a dot action, and it's just the usual dot action. You shift by a row hat, and I forget to check here. Yeah, this is the formula for the dot action. Okay, any questions? All right. Now let's go to admissible representations. So basically, they refer to highest weight representations for the affine algebra with the highest weight, which will be called admissible weight, and which is going to be defined here. And so you take a weight lambda, and you define integrable weight system, integral root system corresponds to this lambda, which is just you take all the real roots such that if you pair it with lambda, you get an integer. Okay. And then a weight is called principal admissible if it is regular dominant. That means if you do the row check and pair it with alpha, any positive root, it doesn't belong to 0, -1, -2. Okay. It can be positive or it can be any other complex numbers as long as they're not integer native. And then you require there exists an isomorphism on the carton, which gives an isomorphism between this root system and the real roots of your initial affine algebra. Okay. So in some way, these admissible representations are like non-integrable representations, but somehow the root system combinatorics behaves as if they're integrable representations. Okay. And a level is called principal admissible if it is the level of an admissible weight. And such level has been classified. So you can only get the level of the following form. So K plus H. So remember H identified with the dual constant number of the affine algebra considering. And it has to be P over U, where PU are positive integers. So they're prime to each other, and U has to be prime to so-called the lacing number of your affine algebra. So basically, the R here is 1 for type ADE, it's equal to 2 for type BCF, and it's equal to 3 for T2. This is also important. And then you ask P to be bigger or equal to the constant, to the dual constant number H. Okay. So this is the only cases where you have admissible weights. And the case where P is actually equal to H is called boundary admissible situation. Okay, so this will be the case I'll be interested in. Okay. Before I move on, any questions? So from now on, I will consider the case where K plus H is the P is equal to H, so it's H over U. U could be any positive integer which is co-prime to H that I fix once for all. Okay. And then I will denote by admit K to be the set of principal admissible weights of level K. And you can convince yourself rather easily that K times lambda 0 is admissible because basically you need, so it's regular dominant, and then for this isomorphism, you just keep identity on the finite part and you just rescale the lambda 0 part. So yeah. And then of course there's a there's a bunch of admissible weights you can obtain just by acting on the K lambda 0 by elements in the extended affine Weil group. So the action of extended affine Weil group stabilize the positive root, the root system, and so so when you do this, kind of the second condition is automatically satisfied because the isomorphism. Okay, so this condition you just twist it by the W action and then you get the desired linear isomorphism. And what you need to make sure is only about the regular dominance. And this turned out to be a condition that you want your X to sense a particular set of affine roots to the positive affine roots. Okay, and this set here is the following. So you have all the simple roots as finite simple roots as before, but for the alpha 0, you need to replace. So before you get minus theta s plus k, and now you get minus theta s plus u times k. I wrote delta before, but delta and k are the same. It depends on what, if you look at the co-root or root. Okay. Any questions? So and then Katz and Wakimoto in 1989 is their first paper where they study all this stuff, and they prove that actually these are all the admissible weights of level k. To just get k lambda 0 and acted on by certain elements in the extended affine wild group. Get this. And then there was more precise result by Franco, Katz, and Wakimoto, which tells you that actually the set of admissible weights can be identified with the weight lattice quotient by u times the weight lattice. And the way it goes is that you take a weight b, and they show that there exists a unique element in W semi-direct with u times q, such that t minus b times this element satisfy the condition that it sends pi u hat to positive roots. Okay, and so this thing here is well defined. This is just this element dot action on k lambda 0, and here therefore you get a representative of such a weight inside the coset of extended affine wild group quotient by this thing. So you get something like p over uq, and then you check that somehow the outer automorphism group acts on the pre-image. Yeah, modulo some details about automorphisms, you will obtain in this way an isomorphism between p quotient by up and admissible weights of level kappa. Okay. And for example, from here you can see quite easily, where's my pointer? Here. So from this you can see quite easily that this set is finite and its cardinality is just u to the power of L, because P is a lattice of rank L. And here I give you an example for SL2. In this case, the Coxeter number is 2, and so our K will be -2 plus 2 over U, where U has to be co-prime to 2, so U is the odd integer. And in this case, you can check that the admissible weights are of the following form. So you have K lambda 0 minus 2J over U times lambda 1 is the finite fundamental weight for SL2, and J can only take value between 0 and U minus 1. Okay, and you can obtain it in two ways. So either you apply the translation T minus J lambda 1, or you apply T times U minus J times lambda 1 times X. Yeah, just give you a feeling about these admissible weights. Yeah, any questions? All right, and so another way to think about this, because I told you at the beginning there's some vertex algebra hanging around, and where it comes is the following. So you consider there is a famous vertex algebra which is called universal vertex algebra. You do the induced representation from CK lambda 0 of this parabolic subalgebra, where G check Z just acts trivially, and the action of K is determined by it acts by K, by this K, and then the X trivially. And so you induce that to the entire affine linear algebra. This gives you a so-called universal vertex operator algebra. And it has a simple quotient as a vertex operator algebra. And those admissible, these are the irreducible representation with highest weight and admissible weights. And these actually identifies with the modules over this vertex algebra inside the category O for the affine algebra. And it is proven by Arakawa that this is a semi-simple category. And the way, like in language of vertex algebra, people say is that this vertex algebra is rational in the categorical. Okay. So yeah, so that's the vertex algebra, which comes in for the admissible representations. Now I'll go to the elliptic affine Springer fiber side. Just to simplify this talk, we will be considering a non-simply laced case, because otherwise I need to introduce all this twisted affine flag variety, etc. It's just too many notations. But it works in the non-simply laced case as well if you take twisted affine Springer fibers. So now we're working on side for G, and so we'll take the capital G to be a connected algebra group of a joint type whose Lie algebra is the one we started with, and then we take the corresponding Borel subgroup and maximal torus, and then you have a affine flag variety, which is the quotient of all the like C double parenthesis Z points in G by the Iwahara subgroup. And the Iwahara subgroup is the same one as what Peter introduced in this talk. Well, if you've seen this, you know this. If you haven't seen this, it's not that important. You just think of this as an affine analog of the normal flag variety that you know. And here, since I'm taking the group of a joint type, so the connected components of this group actually identified with P over Q, and it acts on the affine flag. And now I need a fiber, so I will need to take a particular element in the Lie algebra. Yeah, I didn't write okay, so here my gamma. My gamma belongs to the Lie algebra G double Z. And here you have root vectors for each real root. And so this E something is, for the E alpha I is the root vector in the root space corresponding to alpha I. And so I just take sum of I equals to 1 until L E alpha I plus a root vector in this, for this particular root alpha 0 dot, which was, so this alpha 0 dot was delta minus U delta minus theta S. And so this thing you can identify it with the root vector f theta S times Z to the power of U. So this is, for people who are familiar with it, this is a homogeneous elliptic element. And the Springer fiber in terms of points is just, so it's a subvariety in the affine flag variety. You index its points by cosets by Iwahara, and you just take those such that, so it's G times I, such that if you apply the adjoint action of G minus on gamma, you still get an element in the Lie algebra of I. And you can check, in this case, this is a projective variety of finite type. And moreover, you get a C star action on it, but in the following way. So we have this action of this T double parenthesis Z on the affine flag variety just by left multiplication. And you have a so-called loop rotation. So C star rotation, it just acts as follows. So you take an element, so your element in this group can be represented in this way. So yeah, like G with, you take, yeah. And for GI, you can just think in terms of the formal sum of matrices with the powers of Z, and then your loop action is just acting on this variable. So this is the C star rotation action. And inside you will send the C star in the following way. So it sends into T double parenthesis Z using the co-character correspond to U times row check. And then in the rotation part, it goes to T to the power of H. Okay, and you can check the C star action stabilize this fiber, and the fixed points just coincide with the fixed points in the affine flag variety you pick those which are actually stays in your fiber. Okay. And it's well known that the T fixed points in the affine black variety matches with the extended affine well group. And you can check with not so many difficulty that those which belong to this fiber are actually those elements such that its inverse sends this positive roots to this pi u hat to the positive roots. So from there you see some correspondence, and indeed if you so from this it makes sense to define a map from the fixed point set to admissible representations just by sending an element x to the weight corresponds to x inverse. And it actually induces a bijection between the sin star fixed points in the neutral component of this Springer fiber and the set of admissible representations. Okay, so I could have started with a simply connected group, and then I would just don't need to take this neutral component, but it's just more natural to take the adjoint one and do it in this way. So this is in some sense the expectation from the physicist I mentioned in the beginning in this boundary admissible case. Are there any questions?
So again, what is lambda x inverse?
Yeah, so lambda of something. So for any elements in the extended affine well group, so my notation for lambda x is just x dot action on kappa of lambda 0. So I use this short notation. Other questions? Okay. So if not, I'm going to the modularity part. And so, right, so to set things up on the representation side, what you do is you consider in the weight space, those elements whose pair with the central element has a positive real part. And you can write it in the following way. So it's just 2 pi I. So it's a notation like z tau t, like this notation stands for the element 2 pi I times z plus t times the central element minus tau times b. And z is in a finite dual carton. And tau and c are complex numbers, but you require the imaginary part of tau is positive. And you have an action of the modular group SL2Z here, such that a 2x2 matrices with integer coefficients x in this way. And yeah, it's not important to remember it at all. It's just similarities with those coming in modular forms, and that's the only thing you want to notice. And then, so therefore, this induces an action of SL2Z on the space of holomorphic functions on this space Y. Okay. And then, just like what you do for like integrable representation of affine algebras here, for any admissible representation, admissible weights, you take, as I said, the L lambdas, the irreducible G hat representation of highest weight lambda, and you define a normalized character of this thing by taking trace of element. You take V an element in Y, which is part of this affine cartine. You take exponential of that, take its trace, and you renormalize it by a certain factor. So I think we don't need to care about these details. And you have a renormalized character for each of these representations. And the point is that, so first of all, they're linearly independent. And the subspace they span inside these holomorphic functions on Y is invariant under the SL2Z action we discussed before. So this is like the modularity property of these characters. And moreover, so Kac and Wakimoto have described explicitly how does the generators of this group acting on this basis. Okay, we know it's generated by S and T matrices, which are the two matrices given here. And you can write out the matrix coefficients of these elements acting on spaces. Okay. And so next so this is the the representation side, and now I'll move to the fiber side. And on the fiber side, I need to talk about double affine Hecke algebras, and this probably is the most closest point, I guess, to this conference, right? More about Hecke algebras, affine Hecke algebras. I have some here, but you don't need to care about its definition. I just want to give it here to give you some feeling about it. But so you have a parameter space. There are two parameters, Q and T, and yeah, you need to add certain yeah, you need to be able to take 1 over m roots for this Q. So yeah, so this m is the minimal integer such that when you do the pairing between weights, it's 1 over m times z. Okay, and the double affine Hecke algebra associated with our this finite well group is an algebra over this ring, which is generated by so you have TIs. You have some TIs for I from 0 until, sorry, I think here should be an L, and omega, and so they generated a copy of affine extended affine Hecke algebra, which we have seen in Vanessa's talk. And then you have yet another polynomial generators, right? And then those are denoted by XB, and you have some normal commutation relations between TI and XIs, and some other commutator relations between omega and X, which involves the Q. So yeah, so we won't need the precise definition. I just want to present to you, so you know what this algebra looks like. And so as affine Hecke algebra has a polynomial representation, the double affine one also has a polynomial representation. So it acts on polynomials in X. And we will be interested in a particular specialization of those parameters. So I'm going to take t to the power of h is equal to q to the power of minus u. So the h was the constant number and u was the one we fixed, which is co-prime to h. And for the moment, we'll assume q to be generic. And in this particular situation, this polynomial representation admits a unique finite dimensional quotient, and this I will denote V daha. Okay. So this V daha is a perfect representation in the sense of Cherednik. That means, so it's finite dimensional, non-zero irreducible representation, which has some self-duality, semi-simpliness with like one of the polynomial generators actions and pseudo-unitary representation. Like all these are the names which we won't care in this talk. But the most important thing is it has an action of a central extension of PGL to Z. Okay. So if you want, where I need to cite this things that this is proposed by Cherednik as a sort of abstract Verlinde algebra. So in some cases, you recover the Verlinde algebra comes from the fusion category for quantum groups at union of roots of unity. But from Cherednik point of view, this is just a representation, like a vector space with a few nice structures, like in the usual Verlinde algebra. And it comes up as a particular representation for daha. Okay, and so we'll discuss about this PGL2Z later, but what I want to mention, so where it connects to our story, is that you have a geometric realization of this perfect representation. So first of all, you have a geometric realization of the double affine Hecke algebra using some K-theory of affine-Sternberg variety. So this is due to A plus 4. And then by the usual theory, this algebra acts by convolution on the K-theory of affine Springer fibers. And so we can consider its action on our particular affine Springer fibers. And in this case, it produced, up to localization, produce exactly this V daha. Okay. And also up to you have localization in K-theory. If you do C star equivalent K-theory, then up to localization is the same as C star equivalent K-theory of its fixed points. And since we're in a case, the fixed point is isolated, so these are nothing but just the functions on those points. Okay. So in this way, from the Cherednik point of view, I get an action of PGLC2Z action on this space. And so, so as I said, so this, you have a natural basis of this Vidaha, which is just given by the characteristic functions at the points. Okay, so I have this Chi-W, which are just at the point W is 1 and all the other points is 0. And so they form a basis of this Vidaha. And this P, okay, so did I write P? It's not easy. Okay. So this group acts, its action can be described explicitly. So what is this group here? It's just generated by 2m and sigma tau plus and satisfy this relationship. So if you want to compare it to SL2Z, SL2Z is a quotient of this group by the relation sigma to the fourth is equal to 1. Okay. And the claim is the following. So you can renormalize the spaces in such a way that you you can check that this action actually factorized through this SL2Z action when Q is when the parameter is taken in an appropriate way. Okay, let me see it. So yeah, the second thing about the modularity is that now we specialize Q to a root of unity of the following form. So Q is minus 2 pi I H over U. And then according to my previous condition on P and Q, so here, if I specialize Q to that thing, then T will become 1.
So when you have your starter base in the string of functions,
yeah,
what does it correspond to on the case user? Isn't it like a normal fixed point basis?
It's a normal fixed point basis.
Localize?
I localize, yeah. So like, yeah, here I localize. Yeah.
So
no worries, yeah. So right. So if you put this specialization, and then by the bijection between admissible representations and the fixed points, I have a natural linear isomorphism between the two vector spaces. I will just send the basis corresponding to characters up to some sign to this spaces Chi-W. And I claim this bijection commutes with the SL2Z action. Okay, so that what I mean by like the compatibility for the modular group action. So in some sense, I like this because this V-Daha Verdina algebra is some kinds of construction only as representation of Dahas. A priori, you don't have a like category behind it. But here, on the other hand side, you get a category of admissible representations. So you can interpret this SL2Z action and whatever the fusion coefficients coming out from there in terms of this admissible representations. Okay. So that gives some sort of interpretation for this Daha representations.
Is there some, for certain elements in SL2Z, can you say kind of what operations on the category of admissible representations give rise to it? If you look at the category of admissible representations, and there's supposed to be something like a SL2Z action on that. I mean, does that mean anything?
I'm not sure. You have fusion coefficient, although it's not really a fusion category. But yeah, I think no, I don't know how this SL2Z action is categorized as. It's like in usual fusion categories, you don't have an SL2Z category by the SL2Z action. So yeah, it's in the same spirit as Mathas. Yes. Okay. Are there questions? Okay, and then I want to discuss reduction to W-algebras, but for this part, for the moment, we only look at the simply laced case. There might be might be analog. Yeah, I mean, it's natural to expect there are analogs in the non-simulated space as well, but we didn't look into it yet. And so the relation is the following. So for W-algebra, you need to take a nilpotent element, and we'll assume this element to be even and regular in AB. And then the W-algebra which comes out will be a quantum dreamfield so-called reduction of this simple vertex algebra discussed at the beginning. And from this reduction, you have a so-called BRST cohomology functor, which it's a functor from modulus over this VK of G check to modulus over this W algebra. And then Frankel-Katz and Wakimoto give a criterion which tells you when a simple module is not killed under this functor. Okay. And then Katz, Run, and Wakimoto has a conjecture about when so the conjecture is the following. So they say that if a simple module is not killed, then its image is still irreducible. The first thing. And the second thing, they give a criterion for which simple modules their image would coincide. Okay. And these are proved by Arakawa when your nilpotent element is a principal nilpotent in arbitrary type, and for any F in type A. But as far as I'm aware, this is still open conjecture in general. But on the fiber side, you can do the following. So now you have a nilpotent element which is regular in Levy, and you can take a parabolic for that Levy, and then you can define a parahoric subgroup inside this group G double bracket Z. And then, so remember our affine finger fiber before was here, you take the quotient of the loop group by I, and you require the adjoint action of G minus 1 on gamma belongs to the Lie algebra of I. Here, we introduce not we, but like there is an analog of affine spatiation variety, where you take points in this parabolic affine flag variety, but here you require not this element belongs to the Lie algebra of P, but it belongs to the radical of the Lie algebra. Okay. And you still have a C star action as before. And the thing we can say is that this Katz-Run-Wakimoto conjecture is equivalent to say that you have a bijection between irreducible representations of W algebras and C star fixed points in this affine spatiation variety. Okay, so basically, the way it goes is that you want to check, when a module will die, and that would match this condition. Oh, sorry. So here, like you have this radical is smaller than radical of the Iwahori. So you remove some points from there. And then you want to check when does two simple module coincide, and that's when like 2 points in the flag variety goes to the same points in the parabolic affine flag variety. So those conditions match up very well. Yeah, but yeah, I don't know enough to tell you more about the Katz-Run-Wakimoto conjecture. I just tell you that there's a very nice geometric picture for that. But an interesting consequence is the following. So if you know this, then we can compute the number of irreducible representations for the W algebra, because we know how to compute it for the C star fixed points in this affine spatiation variety. And you get an explicit formula like this. So here, let me explain. Here, what are the things? So WF is the wild group for this Levy, okay? And then R is the rank of G, so it should have L. And then E1 until EJ are the exponents of this WF, of this wild group for Levy. Okay, so you get a formula, you get an explicit formula like this. Any questions?
Do we know such a bijection exists? Or you're conjecturing that such a bijection exists?
So like this bijection should follow from the previous bijection. Yeah, like I'm saying that the condition on the reduction here coincides with the reduction you can do on fixed points. So if their conjecture is true, and then you have this natural bijection. Like, or you can say in whatever cases it's proven, we have this, but yeah. Okay, and also there's a natural compatibility with the SLZ action with this sort of reduction. So yeah. And yeah, maybe to end, let me just mention that there are some cases of such identification which has been established for the Virasoro minimal model. This was by Kozak, Shakirov, and Yan. And then for the WNN minimal model, there's a recent paper by Gukov, Korotiev, now Wata, Pei, and Sabri, which established this. Okay, and then to end, like we computed also some examples in the so-called non-admissible cases where, because from this picture you somehow know that you want to understand whenever you have an elliptic affine Springer fiber, does it have some meaning on the representation side? And so the one we consider is a very particular one, like the elliptic regular number is given by the Coxeter number, and so we had this. But you get some other elliptic regular numbers which are smaller than the Coxeter number, and so you're in a case which is non-admissible, and there are some results in this direction from the VOA side, and we have tried to match up their representation in fixed points in some particular cases, but this is still very at a very beginning stage for the moment. Okay, and I guess that's all. Thank you.